But I'm still going to demonstrate real quick. And this is really something I shouldn't do, because all the people who did do this, they're getting screwed right now. That bugs me. The left half of this bar has mass 1/2 m, and the right half of this bar has mass 1/2 m. Center of mass of the left piece of bar is at 1/4 L. And the center of mass for the right bar is at 3/4 L. The moment of inertia function is to add each piece of mass times their distance from the axis of rotation squared. It's all you had to do. So any idea that this was a lot of work and you had to work on your cars really is going to sound silly here in a minute, because it was 1/2 m times 1/4 L squared plus 1/2 m times 3/4 L squared. There, you did it. Now, because you are solidly smart-ish kids, both of those have an ml squared in them. So I'll take the ml squared out. And all that's left inside now is 1/2 times 1/16 plus 1/2 times 9/16. Being that I know you guys can add, that's 1/32 plus 9/32. So it's 10/32 ml squared. Hurry, look at the screen and write it down. But understand that that was not very much to do. In the grand scheme of things, this is the amount of time it would take you to ponder not doing your car yet. So there we are. Now, do it for the 4 pieces so you can have an appreciation for what we're about to do today. Not now, because what we're about to do today is actually challenge. The only calculus we will do today, and I use we loosely, is that. That's the only calculus we will do today. I believe that 100% of you can do this calculus. I believe it so completely that I'm unwilling to walk around and check, to be disappointed in those of you who can't. Do you understand what I'm saying? Because now that I'm in one of those moods, I don't want to walk around and be disappointed. I'm already starting that way. But you should be able to do the antiderivative of r squared. Now, I did this in 6th period, and I walked around and was disappointed. So, we did all the stuff necessary for this. The antiderivative of r squared with respect to dr means I take r, make it the important variable, recognize it's a polynomial, add 1 to its exponent, and divide by the new exponent. We've done it many, many a time. Now, all the people that are in calc are frustrated that I didn't write plus c. So be frustrated, because all of ours are going to be definite integrals, and there will be limits. So I don't have to worry about your plus c. And keep your c to yourself. What I want to teach you how to do is find the moment of inertia of a group of basic shapes. The rod about the end and the middle, a disc and a hoop, both about their center, spun like that. And eventually, maybe if you're really into this and you love the math, and I do, maybe spinning something, kind of different, like spinning it on its end like that. That's actually interesting mathematics that I actually like. The rest of these really aren't. Now, I'm going to do something that no one ever did for me. and I've looked on the internet for this. There's some resources out there, but it took me 15, 20 years of just banging away at it to figure out the way in which I want to present this to all of you. This is not in calculus. This is not in differential equations. It's not in a math class. You see, the formula for finding the moment of inertia of a continuous object is the summation. You add up every piece of mass, dm, that's the piece of mass part, while multiplying by its distance from the axis of rotation. That's what R stands for. Be careful, very careful, about how you deal with R here. We're going to look at simple examples. But you have to understand what R means. R is the distance from the axis of rotation. This is not the same definition as center of mass. When we did center of mass, which looked like this, if you'll recall, R was the distance from the reference point. Right? You understand you may not understand why that's different. I want to show you why that's different. R is reused all over the place. Some of you still think R here stands for radius. Can't help you. All right? If that's you. It's a placeholder. All the equations on the equation sheet use placeholders. You're responsible for understanding what those placeholders mean. Maybe put it is the perpendicular distance. But even that doesn't really describe it. It's really the shortest distance from the axis of rotation to your piece of mass. So, let's say I wish to find the moment of inertia of a door. Right? Maybe this is a low door like a gate. Now, there's a lot of ways to spin this rectangle. If I was going to spin this rectangle about a point, say, here, what do you mean about that? What do you mean, Mr. Shelton? Well, spinning it about that point could mean spinning it like this. So it shouldn't be in the upper left. But anyways, what if I want to spin it like that? That's like taking this piece of paper and spinning it like that. Right? Well, except it wouldn't be flimsy. That's different than having an axis that runs along this edge and spinning it like this. Do you understand how those two things are different? This would be like the axis of rotation of a hinge going about one edge of this rectangle. So, again, having a physical example, this is one of those, and this is another. Do you believe those two things would have the same moment of inertia? There's no reason to believe they would, especially considering that R is different for each of those. If I'm to pick a single piece of mass, that's what dm stands for, a single piece of mass somewhere in this rectangle. Well, if I'm talking about spinning it like this, R would be measured this way. And I think you could all agree then that every piece of mass under this circumstance would have a different R. Agreed? But if I'm talking about spinning it like this, about the other edge, well then R is measured from the axis of rotation. So all of the boxes here would have the same R, and all of the boxes here would have the same R. So are you beginning to understand how you have to interpret what is being said And be careful about what r means. It's the distance from the axis of rotation, which is a line. So if you want to help we are going to example, you're going to label a box somewhere here and call it dm. If it's a volume, you're going to label a cube somewhere in the object and call it dm. To do something simple. I want to do the rod spun about an axis about its end. We know the answer. You have two versions of the answer already. 1030 seconds ml squared, right? Breaking it up into two pieces, 1030 seconds. We're going to see what the actual value is for this. I'm going to give you a series of steps because what we really want to do is use the formula. But that formula needs a lot of help to be useful. So, first, step one, you need to identify your structure, decide on its symmetry, and determine its density. I know that sounds like 3 steps. It's really just 1 step. Determine how you're going to handle the object and what is its density. Now, this object looks one-dimensional to me. It's very long compared to its length and width. So I am going to treat this object as if it has one-dimensional composition. And I'm going to establish that it has a linear density, a mass per unit length. If my object looked more like that was more like squared off, like that, well, then I probably wouldn't say that. I'd probably treat this object as a 2-dimensional object. And therefore, I would say it has an areal density or a surface density. And if it was clearly a thick boy, I'd probably go with a volume. Treat it like it has a volume. What we're establishing with this determination is how we're going to handle the basic shape of the object and its mass. Like I'm gonna make some assumptions here. I'm gonna assume the whole thing has mass m and length L. Means of placing limits on the size of the object in variables that make sense. L makes sense for an object that's long, and m for mass. Now it is plausible you'll be given an expression for the linear density. If you are, you have to use their expression. Their expression might have something to do as a function of its shape. Maybe it gets thicker as it goes from one side to the other, or more dense as it goes from one side to the other. I can think of examples of that. We had examples of that. That is the triangle problem. Right? It became more dense as you go from one side to the other, thicker, heavier. Or if it says that the object is of uniform density, then you can create the density by placing the mass over the entire size of the object. Now, for us, we're going to be creating densities. For one-dimensional objects, it'll be mass over the entire length. Lots of objects can be treated as one-dimensional. For two-dimensional objects, it'll be the mass over the area. We'll have to find a way of computing the area, getting us an idea of the size and shape of the object. And for three-dimensional objects, it'll be the mass over the volume. So we might have to create the density or an expression for the density. Yep.
We only create it if it's uniform density, right?
Yeah. There's probably no way for us to do it otherwise. So if they tell you that the object is of uniform density, then you're probably going to be creating its density. All right. So for this problem specifically, we have an object of uniform density. We've defined its shape based on it being one-dimensional, and that density is going to be mass over length. Step 2. I want you to identify a single infinitesimal piece of the object and call it dm. Now, we've done this. We did this yesterday. When I said to break the object into 2 pieces and treat each piece like a point mass, we were doing that. But this time, we are picking a random just piece of the object, and we are saying that I don't know the number of pieces I'm breaking this into. However, I'm going to say that this piece has mass dm. Delta m is a piece of the mass. I am saying out loud, I'm going to break this object up into equal pieces of mass, all labeled dm. My integral is to add all of those pieces of mass together. So I'm breaking the object up into pieces of mass, all of equal size, called dm. I want you to physically describe it in your drawing, meaning find a place on your drawing and label that piece dm. This is going to help us establish how to use dm correctly in the integral. So identify a single piece. Now, look, if it's a box, like I said in the... Now, step 3 is very simple, kind of, but can be really complicated if you're not great with the idea of coordinates and coordinate systems. How are you going to point to dm from your axis of rotation? Now, I'm not going to write all the little things that have to go into this. There's a few little things. You should write them. But you need to choose a pointer that can point out where dm is. And whatever pointers you choose to use, those pointers have to be able to identify the first piece, the last piece, and everything in between. Now, I have a one-dimensional object. I'm pretty sure that if I say that that piece is located x away from my axis of rotation, that I could use x to indicate the first piece, 0, the last piece, L, and every piece in between, as long as x is less than L and more than 0. You follow along? Does that make sense? Now, it makes sense now, but... So, how will you point to your object? Okay, step 4 is the hardest. So, I'm willing to write that over here and then erase it. Step 4. Because this is where the magic really has to happen. Get step 4 wrong, no chance of saving it after that. Step 4. We want to express dm in terms of density and our pointer. We want to express dm in terms of density and our pointer. Now that's a lot, but it's not as much as it might seem. Our density is known to us. It's a mass per unit length. Now, regardless of what we have for density, we have decided from the very beginning of this problem that our object is linear, has one-dimensional symmetry. It's linear. So, if I can describe this object in terms of its length, when I say object, I mean our piece right here. If I can describe our piece as a length, then it should be the ratio of the mass of dm to the size of that length. That ratio should be the same because it's density. Density is mass per unit length. So all I need is something that tells me the length of the piece of mass dm. Well, that's not hard. If I'm going out a distance x, it seems to me that this piece is just a little more in the x direction. I'm going to name it dx. So express dm in terms of its density and our pointer. So I have now decided that my size of that length is going to be dx. If this was two-dimensional, it'd be the size of the area. If this was three-dimensional, it'd be the size of the volume. My pointer is x, so my size of my piece of mass is dx, which means if I solve this for dm, I get that dm equals lambda dx, or m over L times dx. Step 4 is quite possibly the one that's going to be the most complicated for you to understand. At the same time, once we've done step 4 for every possible shape, it's the same for all subsequent shapes that are the same. So as long as we come up with one way of writing these shapes, all the other shapes have to be exactly the same as this one. But okay, that's that. We're on to step 5. And here's where things really kind of accelerate. Let's get all this out the way. And here we go, step 5. Assemble the integral. There are 3 parts to assembling the integral. Assembling the integral. First, decide what r is. We've already done this. We've spent a lot of time thinking about it, so this part should be easy once we get here. R is how you point to each piece. Two-dimensional objects, that might be complicated. One-dimensional objects, that's going to be easy. We have decided that we're using x to point to each piece. So that's where I will start. I will replace r with how I am pointing to each piece. You'll notice I keep going to aid all of these determinations. And more importantly, because I have dm equals m over L dx, I need whatever this is to have these variables in it. That's why it's important to be careful here and cautious. Next, just substitute in what you have for dm. Last, set your limits. If it's one-dimensional, which this one is, where's the first piece? Where's the last piece? If it's two-dimensional, then you might have 2 sets of limits. If it's three-dimensional, you might have 3 sets of limits. Don't be afraid of seeing a double or triple integral. That's going to happen. If you have 2 dimensions, you'll have to integrate in 2 dimensions. That's 2 different sums. Luckily for us, our objects are going to be separatable. You'll see what I mean when we get there, but we're not there yet. We're done. That's the rough stuff. Step 6 is integrate. That's the only time you need calculus. Everybody who's in calculus knows that none of the stuff we just did was in calculus. The only thing that's in calculus is that. That's in calculus. And so all of you who are in pre-calc, well, this is the only place where you're at a disadvantage. But like I said, you've done this before. Take anything that has nothing to do with x and pull it out of your integral. We know how to do this integral. I say we collectively, but I know that answer might not be true. But I'm hopeful. I'll take the antiderivative of x squared, which is 1/3 x cubed, and I'll remind myself that I still have to insert the limits. Inserting the limits means plugging in L for x, subtracting and plugging in 0 for x. And that's it. You have done the calculus. So now you have finished solving for the moment of inertia. You'll probably notice that you can reduce this, and that will often happen. And that is the moment of inertia for a bar rotated about one end. 1/3 ml squared. Funny, because if you break it up into 2 pieces, you get 10/32 ml squared. Pretty close. I bet you guys who did the 4 pieces got something even closer. Just be nice, because last year I made them do 10 pieces and then 20 pieces. And there's a little bit of, oh gee whiz, that's a lot of work kind of thing with those 2. So, I had hoped we'd have enough time to do the hoop. We did not. I'm going to be honest with you. The hoop and disc are tomorrow. Hoop is easy. Disc is a different world. It's 2-dimensional. So we'll do both of them. I want you to have it clear and processed in your notes. And then next week, we're just going to do stuff with this and do a couple of experiments. That'll be kind of nice. But fun times. Fun times. In a few minutes, we're going to look at this one. And you'll have to come up with a way of identifying a piece of mass anywhere in this hoop. That might be easy for some of you. That might be hard. Or imagine one that we are not going to do, which may lay on some homework somewhere. If we say that DM is this box right here, a square, how would you identify where that is? Well, I'd probably say I'd go over a distance x and up a distance y. That might work. But I'm also very familiar with the idea that I could go out a distance r at an angle theta, and that would also tell me where it is. One of these is a better choice than the other. If I was to choose, I would use x and y for this rectangular piece. Because for every x, there's a limit to how big x can be, right? X starts over here and ends over here at w, how wide it is. So every x has a limit. And every y has a limit. Starts over here at 0, ends over here at height. So there's a limit to every x and y. That's rectangular. If I'm going to set limits, that one has easy limits. What's the limit for r for each theta? Well, because for this theta, there's one set of limits on how big r can be. But for this theta, there's a completely different set of limits for how big r can be. R and theta might not work good for this boy. Maybe I would save r and theta for things that are circular, and x and y for things that are square, and for things that are neither, wish. Seems to work for some of you. and I'll continue. If I had chosen to do this square instead, and we're looking at this box here, and I decided I would use x and y to point to that box, then r would have to be the square root of x squared plus y squared. Right? If I chose to point to it using x and y, I would have to use an r that points directly to it. I would have to use the variables I've been given or that I have determined in order to point to that box. So we all know my videos suck. This is day number 2, and I'm just going to add, like right here in the middle, I have no idea where I ended up. So boop, new picture there. So if anybody actually watches this video, nobody ever makes it that many minutes in. My average viewing time is only like 2 minutes of video. So it's like, well, nobody's watching for real. So and I can't post the video I took in first and second period. I swore too much. So that one's not making it. That's not making the cut at all. I was just going over homework, so they don't need that. Although the homework review videos are the only ones that really get watched. So stupid. I don't know why. I should not record. What I really want to do is go back to what I was doing last year, which was broadcasting this so that you guys can have a copy of the board right in front of you. And I keep forgetting to do that. And I'm out of habits. Nobody ever takes out their computer anyways. Blah, blah, blah. I'm wasting my time. Let's get back to this. Inertia. This is about inertia. I say to all the folks in AP Physics 1 that if you understand inertia, you can pass the exam. Because the exam is about inertia. And I can't really impress upon you the importance of the topic. But objects resisting changes in motion and having to be forced to do something, and I'm using that word in the Newton's second law version of that word, having to be forced to change, is what physics is about. It's how we give things energy and take the energy away. It's how we change their momentum. It is, in essence, the means upon which we change our environment. And so when we talk about inertia, the way things respond to these external factors is how things in our environment behave. If you understand inertia, you get that. The problem with moment of inertia, which shows up as inertia for things that are going to be rotating, right? It is the I in Newton's second law for torque. So you apply a bunch of torques, what happens to the object depends on its inertia. The real issue is, well, you work it all out and it came out to be 12. What does 12 mean? You understand what I mean? Like if I tell you the moment of inertia of an object is 12, do you have any idea what that means? You have no context. Even if I say it's 12 kilogram meter squared. Remember, moment of inertia is a measure of how much of the mass is distributed about the point of rotation. And I tell you the answer is 12? You know what I mean? It's meaningless, right? Without any context. I mean, yeah, if I know stuff about torque, I now can figure out what's 12? That's like me telling you I have 12 Deutschmarks. Can I buy anything with that? I don't know the exchange rate. I'm not sure what a Deutschmark is. Or if I go into the gym and I'm going to use 12 kilograms. Or do I go into a burger joint and ask for the 12 kilogram burger? Which of those makes more sense? A 12 kilogram burger, God. Yeah, I want that 35-pound burger right now.
It's the U.S.
Because I'm choosing things that I think will highlight the idea that the number, it's not about the number. We're trying to find a reason why this has value. And oftentimes that value gets lost in the minutia of what it is we're trying to do. I want to show you that for a hoop, the moment of inertia is mr squared. So what am I trying to tell you? Well, I'm trying to tell you that if I'm going to spin this hoop with a mass of m and has a radius of r, that to calculate the way it would behave, its moment of inertia is mr squared. Well, how do you know it's mr squared? Well, there's a process that involves the integral. Meaning I am going to take my object, break it up into a lot of little pieces. I call each piece dm, a piece of mass. I'm going to add up how far away each piece is from the axis of rotation. Add it all together, and that will be the moment of inertia. Okay, well, why do you have to do it for a ring? Don't you know the answer already? You guys understand that doing this for the ring is a ridiculous activity. if I'm spinning the ring this way, and this point represents the axis of rotation, then isn't it clear that every piece of mass is the same distance from the axis of rotation? So I add them all up, and I'm going to get the total mass times r squared, because every piece is r squared away. There's no reason to do this. The point of doing this is about process. Give you experience. Understand how it works. But we know the answer. But that way, when we start the disk, you have context. Do we understand? That's what I want. I'm trying to show you how this is done. Because you need somebody to. So I want to start with what we did yesterday. We're going to pick out a piece of mass, and we did this yesterday. I said pick out a piece here, and I said call that our dm. It came up in class 6th period. Well, this dm eventually vanishes when we do this integral. Yeah, I'm going to have to bring that up to you guys, because that's an issue for some of you. And I know. I mean, let's do me a quick favor. Raise your hand if you're currently in AB. Why does the dx disappear? It doesn't disappear. I'm adding them all up. But what you do there by adding 1 to the exponent and dividing by the new exponent, that's voodoo. Ask anybody in calculus why that's true, and they'll say the same thing. Because my teacher said so. Even though they will spend weeks and weeks and weeks with the Riemann's single whatever-sided summation limit. I don't know. I'm not even going to try. There's a whole lot of vocabulary I don't care about. A lot of famous mathematicians, right? Name one. Really? No one went with Euler? I mean, or Descartes? I mean, there's a lot of good ones out there. All right. Pythagoras? All right. So getting back to this. You want to choose a dm. Now, the dm is a placeholder. It's a piece of mass, but it's a placeholder. We want to describe that piece of mass geometrically so that we can choose something that we can point at the object with and describe that object's size to get to the mass, which is why I said the next thing you should probably do is come up with a means of describing its density. This object has linear density, right? It's aligned. It's just been bent into a circle, so it's got linear density. I will take the entire mass and divide by its circumference. That's going to be its density. I want to apply that to dm, which means I want to change this from being about the mass of the piece to being about the length of the piece. To do that, I want to find a way to point to that piece in a way that has meaning and reference. I don't know if you guys know what those words mean. So let's start with reference. I'm going to pick a place and say that's my starting point. What's a good way of pointing to that? Well, I think a good way of pointing to the starting point is saying go up a distance r. Can you point to the first mass there? Yeah, I'm going to call that 0. Great. How do you point to the dm I have? Well, stay where you are at r. Stay where you are at r. Yep, that works. And sweep out an angle until you get over here. That's how I can point to that piece. I've identified a means to point to this piece. Can I use this means to point at every single piece? R and theta. Will that point at every single piece? Great. So now I want to somehow use R and theta to describe the size of this piece. Well, I know that this piece is a length, so I can say that piece is ds. That's not R and theta, by the way, but S is traditionally used for arc length. And you know, and I know, that arc lengths are the product of the radius and the amount of angle swept out, right? Because you took geometry, and that's how you calculate an arc length in geometry. And I'm just looking at those blank expressions, and the 3 people went to know that, yeah, maybe you didn't learn that, but that's true. But even if you didn't learn that, you did get taught that by me. Same thing. So I'm going to say that ds is the result of using a compass and sweeping out a small piece of area. You guys know what a compass is, right? Not the ones I have on my desk that find north, but the ones that that draw circles. So if I'm holding a compass, I put the pointy end here and the pencil end here. And I sweep out a small amount of length. Everybody follow so far? So I went over a distance theta, and then I went a little more in the direction of theta to make ds equal to r d theta. That's how big ds is. Everybody follow that argument? That's a pretty good argument, I hope. Because remember, small piece of length, and that length is equivalent to a piece of mass. So now I can use all these pieces to come up with the big coup de grace, which is I have to express dm in terms of the density. So dm is to ds as dm is to r d theta, which has to be equal to lambda. Right? Same density. We all good so far? Now, if you want, yes, sir.
Just to make sure it's not what's DS?
A small piece of length.
So we're not talking about DM.
dm is the mass of that piece of length. So this, if I use a pair of scissors and cut this piece of arc out, you follow? So if, say it's a piece of string, and I just cut this piece out, it would have a mass. It's a part of the whole mass of the circle. So dm means d is delta. It's part of the mass. So it's a piece. So the mass of that piece would depend on how long that string is. That's what it's trying to say. And I'm just showing two different ways of measuring that string's length. I could measure that string's length in meters, or I could measure that string's length related to the radius of the circle. I want you to do it related to the radius of the circle because it will have meaning later. Is that okay? That's a good question. All right, so back to here. So we know that this is also based on the whole. So in a minute, I'll give you a choice about whether we do this in terms of lambda or we do this in terms of m over 2 pi r. You can pick. I don't care. Lambda is just a symbol. So now we're on to that step where we assemble our integral. Remember that? The integral is r squared dm. Remember, r represents the distance to the piece of mass. Okay, so in this case, that's r squared. Every piece of mass is located the same distance away, right? So they're all r squared. Now dm, I have to replace dm with something here. I have choices. Do you want to use lambda or not? So I'm going to solve that for dm. If I do it in terms of lambda, then I'm going to have lambda r d theta. If I do it in terms of m over 2 pi r, then I'm going to have m over 2 pi r r d theta. I have to pick one of these two things and stick with it for this problem. Who wants the top one? What's that?
We do m over 2 pi r.
I don't care. It's the same to me. So you want to do m over 2 pi r? That table wants m over 2 pi r. That table says no. Tell you what. Here we go. I am a learned person. Therefore, since I like to satisfy everybody, because I probably have some kind of mental disorder, I will do them in a parallel process. Okay? They have to be the same. So, the next thing I have to do is set my limits. I lost my circle in doing that, but my limit is I'm starting at 0 for the angle. And I'm going to go all the way around the circle and come back to 0. So how far have I gone? Yeah, we're going to use radians. So my last point will be 2 pi. If I want to get every single piece of mass, I start at 0 and I go all around a circle. That's 2 pi radians. That makes sure I get every piece. Remember, the pieces are really, really small. Smaller than a pixel on a screen. And I have the good iPad, so there's a lot of those pixels. So, I'm going to go 0 to 2 pi for both of these. Now, in each one of these, anything that has nothing to do with theta, pull out of the integral, right? Because remember, this is a summation, and every term will have the same constants in it, so you can pull those constants outwards. So on the left side, I'm going to pull out r squared lambda and be left with, r cubed lambda. And I'm going to be left with the integral from 0 to 2 pi of d theta. Owen?
Why do we...
And you have to put your hand up higher than that. I'm blind.
Okay, why radians instead of degrees?
Now, the other side's a little different because 2 of the r's cancel. So that's going to be r squared m over 2 pi, integral 0 to 2 pi of d theta. We still good? All right. Everything up until this point has not been calculus. Factoring could be calculus, I guess, but this is the only calculus, right? We're going to do the mystery voodoo of the integral. Now, it's taking the integral of d theta, but there's no number there. So if there's no number there, what is there? Yeah, there's a 1 there, or theta to the 0 power.
Good afternoon, Griffins. Just a reminder that...
All right, we gotta move on. So we're at the end here. So do you all see that this is going to be theta to the 1 power? Evaluated from 0 to 2 pi on both sides. This is r cubed lambda. And on this side, m r squared over 2 pi, theta evaluated from 0 to 2 pi. Totally got my mojo screwed up there. That's 2 pi minus 0 on both of them, right? So r cubed lambda times 2 pi on that side, and mr squared over 2 pi times 2 pi on this side. I've been really kind to do both sides at the same time, but you understand that now we have to plug in lambda, right? We do know what lambda is. You're going to plug it in one way or the other. So now's our time. So r cubed times m over 2 pi r times 2 pi. And that's going to equal mr squared, both sides. Now, we knew it was mr squared from the very beginning. But now we really know it's mr squared, right? We proved it. We used calculus, kind of. We used a heck of a lot of physics first. But then we did calculus. The calculus is worth 1 point. The rest of this is worth like 4 or 5. Now, the bad news is that all my joking around and everything has made it so that, and having listened to the thing for 2 minutes, takes us away from what I want to do, which is this, the disk. The reason why we need the ring is to understand how we will find the disk. The ring was easy. The disk is hard. The disk is two-dimensional. To understand how to do the disk, I think we take a divergent course. And before we do the disk, we do something about the disk that is known. Meaning, for the ring, you could interpret the ring's moment of inertia and understand why it's mr squared. Knowing that the moment of inertia of a disk is 1/2 mr squared doesn't convince you that the process we're going to do is correct. So what I'd like to do is show you something else that uses the same process and then apply it to the disk. Yes, ma'am?
So is this where we do the double integral?
Yeah. That's what we're going to do. And to do that, what I'd like to do is find the area of a disk using the process that we'll use to find a moment of inertia. Now, I am confident that everybody in the room knows that area of a circle or a circular disk is pi r squared. So we know the answer. I want to prove that this process works. We have to choose a piece of the disk. Instead of choosing a piece of mass, we're going to use a piece of area. Now, trust me, we're going to do area density, so this applies directly to the piece of mass, okay? I'm going to choose a square somewhere on the disk. This is a piece of the area of the disk, and that piece can be found to have an area of length times width. That's how you find area, correct? Everybody can agree on that? So I want to find a way of displaying the length and width of this square. I'm going to still choose this to be 0. But this time, I need to point out every piece of this disk, which means every square. So I'm going to use a pointer that is only r long. And I'm going to point to the first corner of my disk, which is theta away from 0. As long as I keep r within this range and theta within this range, can I point to every single square in the disk? We're out of time. But can you see that I could probably write this as dr? It's a small distance in the r direction. And we already proved this, but this side would then be r d theta. It's a small piece of arc in that direction. Is that good too? So we're going to compute the area on Monday of the product of dr and r d theta, because that should be the length and width. But we're going to add up every square over the whole disk. But we're going to begin right here, and I believe on Friday, I had talked about the fact that we are trying to identify a piece of the mass. And, I called this piece of mass dm. And from here, we're going to try and relate this to the size, structure, and shape of the disk. So I picked a rectangle somewhere on the middle of the disk. And I tried to remind you that area is length times width. And this area would be a length, dr, times a width, r d theta. And that's right where we stopped. Any question from there? All right. If I want the entire area of a disk, then that would be me adding up all of the pieces of the area over the entire disk. That means taking the integral of all of the pieces of area. But my area is a product. Now, you'll notice that there's two integrands here. There's dr and there's d theta. In order to take the area of a product with two integrands, we are going to have to take a double integral, because there are two integrands. There's two d somethings. Now, don't get too worried about this. I mean, having two of those there is not much different than having one of them there. If you didn't know what one of them by themselves meant, then you could just as likely not know about what two of them mean. But don't get too worried about it. We want to add from the inside all the way to the outside. That's one sum. And we want to add from 0 all the way around to 2 pi. That's another sum. So we are doing two different sums. If this was in 3 dimensions, you understand we'd probably have 3 different sums. So I wouldn't worry too much about it. Now, there are times when you should worry, where doing a double integral is not so straightforward. And this isn't one of them, but because I want you guys to be learned people, I want you to understand when you would be able to spot the difference. Right now, for every single theta, we would start at the middle and go to the outside edge, right? Wherever the boxes are. If I was at a theta over here someplace, right, this theta, don't I still start at the center here and integrate all the way to the outside edge? My object is uniformly shaped. Every theta has the same range of r. Now, there are certainly shapes where that's not true. Imagine I've tried to draw this all. Enough of that. Let's get back to here. Because r and theta are not related, what we have to do first is get all of the things that have r in it on the side with r. And what I mean by the side with r, I mean in front of r. And all the things with theta in it have to be in front of theta. There are no things with theta in it. We can split our integrals out now. Integrals are sums. So we're going to sum over r and then sum over theta. But we are multiplying those two sums together. That's what gives us area. And we have limits. We know that r is going from 0 to big R, the outside edge. And we know that theta is going from 0 to 2 pi. Well, that's about it. You guys know how to integrate. So the actual integral portion here isn't particularly interesting. They are independent integrals. So I'm going to do the first one. I have a polynomial function, r to the 1 power. So my antiderivative of r is just r squared over 2. And I'll be evaluating that from 0 to r. And I have nothing in front of d theta, so what does that suggest I should put there? Theta to the 0 power. Now it's a 1. Right, the implied 1, which means the antiderivative will be theta, evaluated from 0 to 2 pi. So, plug in my limits. 1/2 r squared minus 1/2 0 squared. And my other limit, 2 pi minus 0. And when I work this out, I get 1/2 r squared times 2 pi. And not surprising, that just gives me pi r squared. So, proven, the area of a circle is pi r squared. All right? Now, I have a few of you that are in calculus. You should perhaps consider how you might prove the surface area of a sphere. Right? It has to be 4 pi r squared. It's a two-dimensional integral. You could probably do it. You know what you have to do. You'll need polar notations, but for 3 dimensions. So you guys who are in calculus, especially you BC kids, you should consider trying it. It's a pretty straightforward. But I did all of this mostly not to prove that the area is pi r squared, but to show you that this process of doing a two-dimensional integral yields an answer that you recognize. So we all recognize that the area of a circle is pi r squared. Now that we've seen it, I want to hopefully recruit you to believe that we can do this substitution to find the moment of inertia of a disk. Everybody understand? That's what I really want to show you, but I needed to give you something tangible. I mean, I'm going to tell you what the answer of a disk is anyways before we do it, but I wanted you to see that this process works. It gives us a reasonable answer, and it's not just coincidental. So, moment of inertia of a disk. Again, step 1. For moment of inertia, I want to start with some way of dealing with the fact that the object has mass, but we're trying to break it up based on its shape. So the first thing I'd like you to do is come up with a way of expressing the density of the object. So either the density is given to you or you create the density. If we say the object has a radius of r and a mass of m, then the surface or area density of this disk will be m divided by pi r squared. We use the surface density symbol this time. All right, the density per meter squared. Next, identify a piece of the mass. somewhere on this object. Indicate that this is a piece of the mass. Call it dm. Make a decision about how you will point to that piece of mass. I'm going to point to it by setting this point up here as 0. To point to that piece, I'm going to go over some angle theta and out a distance r. I am pointing to a corner of the piece. Now we want to try and find a way of expressing the size of this piece using our pointer variables. So this side, which I see as a length, and this side, which I see as another length, could be used to help give us an expression for the area of the piece. Since we have the areal density, expressing this as an area makes sense to me. So I want to find the length and width of my piece. Now, we did this a little bit already on Friday, but I'm repeating it. If I go out a little bit more in the r direction, then I can have a small piece of r and make that my length. And if I sweep a bit of arc length by staying at r but going over a small amount in the direction of theta, then I will get an arc length equal to r d theta, and that will be the width. Now, my next step is to find a way of replacing dm with something that has to do with the shape of the object. In this case, replace dm with something that has to do with the shape of the object. We're going to basically roll it through the density. So the best way to do that is to recognize that the piece that we have, that little piece of mass, has to have density equivalent to the whole thing. So the ratio of dm to dA has to be equal to the ratio of m to pi over r squared. Now, in this class on Friday, you guys wanted me to do both of these. Either do I asked if we should do the whole thing in terms of the symbol or the whole thing in terms of the ratio, and you guys couldn't agree. So today, I'm not going to give you the choice. I'm going to use the symbol for density in my calculation, and I will plug in the value for density at the end. So what I mean by that is I'm going to say that dm equals sigma dA, or dm equals sigma dr r d theta. All right. So we've done almost all the... I got something on my iPad there. We've done almost all the pieces. We've got our dm now. We've got our expression for our density. We've identified where to start and where our piece is. So now I think we can assemble our integral. Moment of inertia is the integral of r squared dm summed over the whole object. Please remember that this r is a placeholder. It means the perpendicular distance from the axis of rotation. So I think it's clear that this r and this r can be the same for this problem. That r does represent the perpendicular distance from the axis of rotation to where my piece of mass is. But remember, you always need to evaluate that. Do not take it for granted. We're going to do one next where that's not true, but we'll have to be more careful. We have an expression for dm as well, so we can go ahead and drop that in. That's sigma dr r d theta. Now, that's a whole lot of things, and it is 2 integrands, so this would be a double integral to be able to account for all of it. And technically, when written like this, the interintegrand goes with dr because it's on the inside, and the outer one goes with d theta. You choose the order. But we're not going to worry about that because we're going to split it up. All right. So we've done almost all the heavy lifting now. It's time for us to do the calculus. All of this, again, isn't calculus. This is how you set up an integral in order to calculate the moment of inertia. But we do have calculus to do. So let's go ahead and do the calculus. First, collect all the things that have r together and put them with dr, and all the things that have theta and put them with d theta, and anything that's constant over the course of your integral, you can pull outside the integral. So, sigma out front, combine all the r's into r cubed, put them with dr. There are no thetas. And now set my integral. Alrighty. We have 2 separate integrals to do. Pretty easy. So let's do this one first. Polynomial, r cubed, with respect to r. Anybody want to offer what the answer is for that antiderivative? There we go. 1/4 r to the 4th. Evaluated from 0 to r. And there's nothing there for d theta, so we've done this enough times. I don't feel like I have to spend a lot of time reminding you what it is. Now we do have an expression for sigma. We should probably pop it in there. Seems like the right time. And put in our boundary conditions, r and 0, so r to the 4th over 4 minus 0, and 2 pi minus 0. Now, we're done. This has got to be the moment of inertia. We should clean it up, though. I see 2 pi m r to the 4th divided by 4 pi r squared. Now, kind of knew what the answer was beforehand because I told you what the answer was before we started. Well, a couple days ago. But we get that the moment of inertia is 1/2 m r squared. It's a lot of thingy things. Not terrible. But I mean, it's not like you're doing it by yourself without a net. You've got me here, kind of leading you through it. There are situations in which the moment of inertia can be pretty challenging. But I've given you the basic 3. We have the rod about one end, the ring about its center, and now the disc about its center. Stop it. There. There we go. Why? There we go. All right. So, just taking a minute. I want to talk about some basic shapes for just a second and then talk about something a little bit adjacent to this. We proved one of these. Or I guess we proved three of these. We have the rod about its end, 1/12 ml squared. We have the ring about its center, which is mr squared. We have the disk about its center, which is 1/2 mr squared. There's no reason for you to believe me on this, but these two would be pretty hard for you to do on your own. I'm not saying you shouldn't try. We've got quite the smart people in this room, so they should try it. A hollow sphere, maybe like a, I don't know, soccer ball, since that's important in here, 2/3 mr squared. Solid sphere, I don't know how you can differentiate one of these from the other, but a solid sphere is 2/5 mr squared. It shouldn't be a surprise that if you were to rank these from most difficult to turn to least difficult to turn, it would go ring, hollow sphere, disk, solid sphere. When you think about the fact that this is a measure of how the mass is distributed about the axis of rotation. Three-dimensional balls are going to have more mass towards the center in many cases, except the solid sphere is solid all the way through, so most of the mass is by the center. It is the easiest to turn. The disk is the next easiest to turn. We have to flatten it out. So you'll have more of the mass near the center than you do with the solid sphere. More of the mass away from the center than you do with the solid sphere. A hollow sphere, though, all that mass has been carved out of the middle. It's more than a disk because you have more of it on the edges. But a ring is going to be the hardest to turn. Now, I put that it was 1/12 ml squared for the rod, but nobody corrected me. It's 1/3. About its end, it's 1/3. It was a mistake. I'm thinking ahead to what I want to talk to you about, which is the rod about its center. Because the rod about its center is 1/12. Now, these are all the basic shapes. There are others. If you look in your book, there are others. There are things missing from this, though, that I need you to have in your notes. Whether we're talking about a ring or a disc, we haven't talked about the fact that what if you had a ring that was like long? That's not a great picture, but I hope you can imagine what I'm trying to put there. But something like an actual, like my wedding ring, which is wider. It's not just a hoop. If we're spinning about its center, do you realize that all the mass is still the same distance away from the center? If you don't, and that's not a very good thing, think of any tube. If you have any tube, like a piece of PVC pipe, or even a cup if you cut the end off, or a can if you cut off both ends, you'd have just a long ring, wouldn't you? All the mass would still be the same distance from the center. A hollow cylinder in that way would behave like a ring. So it doesn't matter that we haven't said this. If these objects had a height, so if we're talking two-dimensional, you can see that you can begin to build lots of objects, and you really do have kind of a rich pattern of how their moments of inertia will behave. But what you may not know is that you can assemble objects together. Imagine a simple dumbbell. Something like, two large spheres. Connected by something bigger. Say connected by a rod through the middle. So something like this, and you want to say spin it. Maybe this is a rod of length L, and you have a sphere and a sphere. Especially if you were told that this is mass M and radius R for both of these. Wouldn't be able to use the point mass formula because we've been given the shape and dimensions of these objects. So I would have to use the moment of inertia of a sphere, the moment of inertia of a rod, and the moment of inertia of a sphere. Moments of inertia add together. They're not scalar values. It's just more inertia. So we can just add these things together. Kinda. There is one problem. All the moments of inertia we calculated were for specific places on each object. The center of each sphere and the end of one rod. In order to combine these together, we can only add their moments of inertia together if they have the same axis of rotation. Well, we don't have the same axis of rotation, right? We need to get a common axis. For the sphere, we want the axis of rotation to be here. We don't have that. We have it about its center. Now, luckily,
Teachers and students,
luckily, there's a way around this. We don't have to recalculate the moments of inertia. There is a theorem called the parallel axis theorem. I'm going to write it down anyways. And I'd encourage you to write it down. That says that we can shift the moment of inertia to any parallel axis by taking the moment of inertia through the center of mass and adding a shift Now, it's on your equation sheet, but I wrote the word shift distance in here because they just put another R here, and that just makes it tough. So we'll come back to this tomorrow and pick this up. Again, a cylinder that was long. If it were hollow inside, or if it were solid, we would still treat it like a ring or a disc. Because even though it has a height, it's still about the distribution of the mass away from the center. So since the mass is still distributed the same way, we would still treat it like a ring or a disc. Similarly, the door. The door is just a rod spun about one end. It doesn't matter that it's really tall. It's still just a meter stick that's spinning this way. We get the inertia from the fact that all of that mass is rotating, but a piece of the door here is the same distance away from the axis point as that same piece directly below it. So because of that, even though these look kind of a pinwheel, now there's 2 pi angles available here, right? But this range for this theta is different than this range for this theta. You follow me on that? In this circumstance, every different theta might have a different range for r. I would not be able to do the process I'm going to show you if r and theta are related. then we have a problem. Then you have to do it different. You would need to know r is a function of theta to be able to do that. This is this picture of a pinwheel, which is not particularly symmetrical, but there is a function that would describe this. And once you guys get into more advanced math, you'll do polar plotting. And in polar plotting, this is a straightforward relationship between r and theta. So it exists. Anybody done any polar plotting yet? It's built into your calculators. You can try it. You know, a circle, r is a function of theta for a circle. It's just r equals a constant. R is the same for all theta. So, you know, that's pretty boring, but there's lots of ways to have them, you know, change. A spiral would just be something where r is linear function of theta. So r is just getting bigger and bigger and bigger as you go outside the circle. So you can imagine a closed pinwheel just being some kind of function of r.